In the previous lecture, we created a parallel program for computation of pi, and we did a scaling study as well. This was the code that we used. Here it has been written for 2 threads, but it can be easily modified for higher number of threads. A scaling study done using the Intel compiler on a machine with specifications given as such is given for up to 4 processing cores. And you can see that you are not getting really the maximum possible speed up that should be possible. We need to ask ourselves, why is there such poor performance in this parallel implementation of trying to compute pi? One of the reasons why this happens is something called as fault sharing. Now, if you go back to the previous code, and you can see that the array sum is actually shared by all the threads. For example, if this was 2 threads, some would be of length 2. If there were 4 threads, some would be of length 4. But this array sum is global in scope and is shared by all the threads. While each thread is now writing only to one individual array location, maintaining consistency, which makes the program correct, but it does lead to another problem where this entire array has now got to be shared with these multiple threads and hence by multiple cores. So what essentially happens is that when you have 4 threads, they will get scheduled on multiple cores. But this array has now to be shifted back and forth from the higher level caches to the lowest level caches. And when thread 0 is trying to write something to some 0, this has to be copied to the lowest level of cache. And to maintain consistency, when thread 2 is writing into sum 2, this has to be then copied back onto the other core's cache. So this will result in some sort of sloshing back and forth between threads, and this is called some sort of fault sharing. This slows down the coding to a large extent, or rather slows down the program to a large extent. So how do we get rid of this? So if we know the size of the L1 caches, the lowest level caches, we can pad it with some extra elements so that we have distinct copies of the memory locations going to different places rather than having the whole thing going back and forth. So if you assume that the L1 cache is of 64 bytes, this is something which you can look up in the processor specifications. You then pad it with extra elements. So for example, now this array sum is the total number of threads and has also addition of 8 elements over here. So every 8th element is where actually the sum is being stored, and 7 elements are just being discarded and not being utilized. One of the disadvantages of this is that it is utilizing higher memory than required, but that's okay in this case because the amount of memory that is required is small. And because you are having it with such alternate memory locations, you will end up getting each of these in a different cache line and hence improving the performance of the code. Now, with this padded accumulator, if you look at the code, you get slightly better performance. As expected, for a single thread, the performance roughly has to remain the same. We get it at 1.86 seconds. As we increase the number of threads, you can see the performance has improved. In fact, for 4 threads, it has dramatically improved. In fact, almost it has halved in the runtime. So this is how you would look at performance and see how memory sort of affects these multiple threads. There are other ways to improve performance as well while maintaining consistency and coherence in the program. So now we will look at certain synchronization constructs using OpenMP. So we can do high level synchronization using statements such as critical or statements such as barrier, and we will discuss this in detail. There are other advanced synchronization operations such as atomic, ordered, flush and locks, which we will look at in the later part of the course. So let's try to analyze what a critical region is. Critical region essentially means that there is mutual exclusion and only one thread at a time can enter the critical region. Now, if you look at this snippet of code, within the curly braces, you can see there's a parallel section. Multiple threads are able to execute this parallel section. Each of these threads have their own data members, but there are also some sort of common functions. You can see that the variable res is common to all the threads, and each of the threads do not have an individual copy of it because it has been declared outside the scope of the parallel section. So when you put in a pragma such as OMP critical and then you have an addition operation over here, what it essentially means is that only one thread at a time can go and call the consume function and then do the addition operation into the variable res. Remember that res is a variable which has been declared out of the scope of the parallel section, and hence it's sort of a global variable, and threads do not have individual copies of the variable res. So only one thread at a time will now be updating the value of res. The other way to do synchronization is to add something called as a barrier. Barrier is an executable statement which executes in standalone mode. It does not do any programmatic operation. All it does is that it creates a location where all the threads will come and synchronize. For example, in this snippet of code, if you look at where the hash pragma OMP barrier is put, while the line of code where BRR ID is being updated, and that's being done in parallel and being done separately by each of the threads, until all the operations above the barrier are complete, BRR ID will not begin for all the threads. In short, what we are trying to say is that each of the individual threads will execute all these lines of code, then wait at the barrier over here, and once all the threads have reached this point, only then the next set of line will be executed. So that's how a barrier works. Now, we can modify the same Pi program to use barriers and to use critical statements so that we avoid the sloshing of independent data. This way, we can avoid using the padded accumulator, which will reduce the memory footprint. Remember, the padded accumulator was creating extra memory allocation just so that the cache lines are not shared. And this way, we can be memory efficient and also avoid the sloshing and the slowdown. So we can now modify the Pi program using all these OpenMP functions like OpenMP get num threads, OpenMP get thread num, get time, set the number of threads, parallel and critical section. A modified code would look something like this. This is the initial code which has the false sharing, if you recall, and this is the timing that we got. So we are now going to modify this program in such a manner that we are able to use the critical statements. Here, if you realize, in the original code, the parallel scope ends before this for loop. So this for loop is being executed by only a single thread, not by multiple threads. And that's how we maintain the consistency in the program. The other parts of this code are being executed by multiple threads, the total number of threads being what we have requested. Now, let us see what happens if we use critical to remove the impact of false sharing. What we need to do now is, obviously, we need to create a scalar sum which is going to create the local sum of the integral for each of the threads, and we need to declare it in such a manner that it is specific to each internal thread and it is private. So we declare it inside the OMP parallel pragma loop. We then compute each of the local sum. Remember, the moment the parallel section ends, this variable sum will now go out of scope because it's been declared within the parallel section. But here we are not having any array, so there is no question of false sharing. Each thread is free to go and compute sum at its own speed and its own will, but it will accumulate only the partial sums. What we have done is that we have created a variable double pi which is global in scope. That is, each of the threads will have only a global version of it. There are no local copies of pi. We then compute the sum of pi using this critical statement. Because sum goes out of scope beyond the parallel region, we must have this statement within the parallel region, but we need to ensure its consistency by putting in a critical statement. So what does this mean is that all the threads will go ahead and do this computation first and will have its respective sums. Their respective sums will be added into pi one by one. Only one thread will be allowed to modify the variable pi at one time. Which thread? It depends on which thread reaches this first. Let us say thread 0 is the first one to reach this line. Then thread 0 will go and add its local sum to pi. After thread 0, let us say thread 3 reaches. So thread 3 will then go and update pi. While thread 3 is updating pi, during that process, remember this takes some amount of finite time in the CPU world. There are some clock cycles that will take. If thread 2 comes and says that it's ready to execute this statement, it will have to wait until thread 3 has finished updating pi and written its value over here. And then only thread 2 will be able to go into this loop, so on and so forth. So at any given point of time, only one thread is allowed to handle the memory location which is associated with pi and do the summing process. This ensures consistency. This also takes care of the global sum calculation, which we were doing it in a slightly different manner. And this also takes out the problem of false sharing. So if you look at the original pi program, which ran about in 1.8 seconds using one thread, with two threads, with padded, if it was using 1.01 seconds, if we use critical, it was using roughly about the same time. But if we increase the number of threads, you can see both the padded and the critical way of programming, both are giving roughly the same time, but they was much better than the first implementation. Now, one would say, what's the big difference between padded and critical at this point of time? Well, because the timing seems to be roughly the same. What is useful over here is the fact that the critical program uses less memory compared to the padded program. And this is quite useful if the program sizes get quite large. So one question that could happen is that what will happen if you put the critical section sort of inside the loop? Now this is a question I'll let you think about for a bit and then try to answer it yourself. What's going to happen in this case? The other way of trying to get parallelism out of OpenMP is to use parallel loops. And we will look at certain constructs of parallel loops at this point of time. Now, what we are doing with loop work-sharing constructs is that it splits the loop operations among thread items using some sort of teams. So instead of having a parallel section, if I say hash pragma OMP for, and let's say that I have to loop over n items, and I'm doing an incrementation of the index by 1 every single time, and I'm calling some sort of a function over here. Now, What it does is that it makes this loop control index I private for each thread by default, and all the threads work will now be then split for this loop, and all the threads will then wait at the end of the implicit parallel loop before they proceed ahead. So there's some sort of an implicit barrier at the end of this for loop. So let's look at an example at this point of time. Let's say that we have a sequential code where we say AI is equal to AI plus BI, and we're doing it for an array of size n. Now, we can write it using the SPMD pattern using this bit of code where I make a parallel section. I say that I figure out what the total number of threads are, I find out what my ID is, and I then divide the work equally between I start and I end, and then do the for in this manner. Now, I have to write at least 6 to 7 lines of code extra to get to this point. Now, I can make my life easier by just saying hash pragma OMP for and putting this for statement underneath. This will implicitly create all the threads that are required, divide this entire array into the requisite number of parts where the threads are given sort of equal workloads, and subparts of this array will be summed by different threads. So this is how work sharing is done in the parallel region using a parallel for construct. Now, you can do a few advanced things over here as well. You can see how to schedule these loop iterations. Now, for example, these loops could be sufficiently large. You could schedule them into sort of chunks or sizes of your choice. Now, you can schedule them statically or dynamically. What do we understand by static scheduling and what do we understand by dynamic scheduling? Let us go back to this example. Let us assume that n is of the size 10,000 and the number of threads we have is 4. And this is what is called as static scheduling. Now, in this case, we are doing only a simple addition, so the workload is sort of uniform, and we expect that all threads will finish the execution roughly around the same time, and hence the time that will be taken is roughly the same. But it is not necessary that the workload be uniform. Depending on the index that you're working with, you could have a higher or a lower workload, which could take different amounts of time. Now, if I have dynamic scheduling, it's quite possible that one thread is working hard because it has a higher workload, and another thread is working less because it has a lower workload, depending on the vagaries of the program. Now, if we take the same data structure, and let's say that if it has 10,000 length and we have 4 threads and we schedule it using chunks of 100, what's going to happen is that let's say one thread takes twice the amount of time of the other thread because of the workload vagaries. If we use dynamic scheduling, the moment thread 1 it finishes its work, it's going to go and pick up another chunk of work, irrespective of whether thread 0 has finished it or not. So it is quite possible that at the end of the program, thread 1 has worked with maybe 50 chunks of data, thread 0 has worked only with 10 chunks of data, thread 2 and 3 have worked with 20 chunks of data each. So what we are trying to say is that the amount of data that each of the threads work might not be uniform in dynamic scheduling, but they roughly try to finish work as fast as possible. If the workloads are same, then it is better to use static scheduling. So what really happens is that in static scheduling, the scheduling is done at compile time, so you don't have to estimate the work sizes, you don't have to figure out what the workload is, so on and so forth. So from a programmatic perspective, it's faster scheduling, but you're hoping that the work is sort of uniform. With dynamic scheduling, you need to put in extra effort to do scheduling during runtime, because if there is a lot of variable work per iteration, you don't know when the threads would finish. So this requires slightly more complex scheduling logic, which takes more time during runtime, but it is done with an effort to finish work the fastest, especially if you have highly variable work per iteration. So one needs to use static and dynamic scheduling appropriately based on the algorithm that one is writing. There are certain other shortcuts as well. For example, instead of using hash pragma OMP parallel and then declaring hash pragma OMP for, where you're basically denoting a parallel section and then writing the for, you can combine it into one same work sharing directive, calling it hash pragma OMP parallel for. Both these lines of code are effectively equivalent. This reduces the load on the programmer a little bit. So how do we work with loops? The main approach that we need to figure out is find out what are the most compute intensive loops. Remember that Amdahl's law also applies over here. We try to figure out where is the maximum amount of work being done which can be parallelizable. That's what we try to say by finding out the most compute intensive loop. We try to make the loops iteration independent, in the sense that each iteration of the loop should not depend on the calculation of a previous iteration. So if this is done, there are no loop carried dependencies, and then you can safely parallelize it without any issues. And then what we do is we place the appropriate OMP directive and we test it. So if you look at a simple programming snippet over here, where I am going ahead and adding the number 2 to every value of j, I can go ahead and make it into a parallel program by using this directive over here. So we try to remove the loop carried dependence in this example. In the next class, we will learn how to handle reductions, because reductions are very common in programs. Here we are trying to compute an average of an array, and this is a standard reduction program. We will look at how to remove dependence amongst different loop iterations, and these sort of dependencies are very common in reduction operations. And we will see what support OMP has for these reduction operations. Thank you.